everybody. My name is Dan Williams. Thank you to him for convincing me to do this. So the goal of all of this was to learn how to interface Python with C. I didn't know a ton about it, and I wanted to get a good idea of all of the solutions that were out there. We decided that we hope that this is useful for you guys too. So, before I go into anything, this is not production code. For all of those reasons, you've been warned. If you copy it, do so at your own risk. So this is the use case that we're going to be playing with. I'm not going to talk a lot about it. I'm assuming you all know how EST works. But the motivation for it was to pick something that's relatively easy to implement, and that I could implement in a bunch of different languages, and I wouldn't mind implementing, it turned out, about 4 or 5 times. Oh, and a little bit more about the test case. We just populated one of these and did a whole bunch of searches through it. So here's the various options we have. The first one, this is the standard interpreter that 99% of you use during the day. If you don't know what you use, it's probably that. PyPy is a drop-in replacement for that. You can use without really realizing you're using something different most of the time. And then we get the interesting ones. So Cython will take Python and then compile that or interpret that into C and then compile it down. And the remaining options are ways of taking C code and Python code and gluing them together without changing either of them as much. So, first one. In case you weren't aware of this, whenever you're writing PyCode and you're importing those modules, they can be either pure Python or C, and they both look the same. So we're going to exploit that these libraries exploit that to provide a nice interface for whatever is behind that backing library. So, like I said, this didn't take too long to do. This is going to be the comparison case, and took about 3.5 seconds to run through 1 million searches in this thing. So, first option, PyPy. Like I said, we're just going to replace the interpreter right here. It drops right in. I ended up having a few difficulties, but it was mostly the learning curve for installing a new thing, making sure I had the settings right. But the speed up is a little bit interesting. So again, thanks to some help from Ned and the Python IRC, because the speed up is run by a just-in-time compiler, which means it's not always on. Right, so the first couple times you run it, it's still interpreting it. Eventually some threshold hits, and it compiles that portions of the code down, and that's right around this period. And that's when you start getting that payoff. So it's useful. I mean, when you're going this far in, if you're doing a lot of loops on it, it'll definitely reflect that speed up, but just beware. And the rest of that is just saying that it took about 4 hours to write the code itself, and setting up PyPy was about an hour. So I've already said most of this. The final 2 warnings are that PyPy and the standard interpreter, they're not exactly the same as far as features and parameters. So it may take you a little bit of fussing about to get the same behavior from both of them. All right, so the first weird one. So like I said, the intent from this, the design goal was to take Python, transform it directly into C, and then compile it, and you can import it as a module. This works okay. Actually, we'll get to that in a second. It works okay, but you get better results when you add certain hints on it, so that the interpreter knows better, the Python interpreter knows how to compile that better. So this is standard Python. This is the more optimized version of Cython. So it's not a lot of changes, but it's it's not obvious if you're coming from Python. And it's, even if you know both Python and C, it's still not all you need to know. So raise your hand if you want me to talk more about the types on this.
Just read the first line, the contrast.
Oh, okay. So the first line is where all the changes are. What got added here was a keyword at the front of it. Instead of defining your Python function with def, it does cpdef, which is specific to Python, which says it's a C and Python function, right, which then tells it to try and compile that in a fast way. And then we add types in front of both the parameters and for the return, so that it's fully defined. So obviously I had to do this for all of the functions throughout the program. Program was like, 200 lines or so. But this is pretty representative of what I ended up having to do. Hope you don't mind. So this is what I was talking about. If you just take Python in, you do get a good speed up. It's not impressive compared to some of the other ones, but worth a try. And then you get a really good speed up if you actually add in all those hints. And this is actually about the fastest one I got in my test case. And then the final point is that it is more complicated, both in learning curve and in fussing about, trying to get exactly the right combination of typing and so on. So like I said, significant speed up, but it is complicated to set up. And probably the worst part about it is that you have to learn a new half language. It's not just Python and C, but like this other one. So here's the next one. This is probably well, I'm not gonna say that. So the next three are you start with C code and standard Python, and you're trying to figure out ways that they can just talk to each other easier. So this would be the C code that you have, either you wrote it or you have an external one. And this is the translation layer, which you write in Python. And it talks to a bundled part of the standard interpreter. So it's a C-types module. The interpreters you guys all have has it included. So that's pretty nice. I'm trying to remember if I have the examples in here. So it works pretty well. You get modest speed up, but it obviously doesn't compare to the other options. And it does take a fair bit of time to manually add in all the bindings. Right. So the one thing that I did find useful was I noticed that you don't have to change the original C code. All of the Python code you write, it's outside of the C code. So that means you can do things like take proprietary binary libraries, or libraries that you don't want to modify because you don't want to take on maintenance burden or something for them. So that's kind of a nice thing, which the other ones don't share. And then, so we can talk about more if you guys are interested, but the bindings for them tends to be somewhat verbose and somewhat repetitive. So it's not my favorite. So this is the great granddaddy of them all. This is all using the batteries included stuff, but instead of using convenience bindings, which translates amongst all these layers, you just use the original API, like the API that the interpreter itself uses. So as you can imagine, this is a lot of C, and this gets very voluminous and you have to specify everything. But it means you can just have everything in one C file, in that one code base, and it talks directly with Python, and it's all neat, conceptual. So this is also pretty fast. But where the other options took me, a couple hours in the morning, this took me pretty much the whole day to figure out. I figured out all the settings you have to do, and all the way different like flags you need to give Python that are not obvious. Fortunately, there are libraries for this. I'm just acknowledging that they exist. Out of curiosity, anyone have a question?
I have a small question. So what are the differences between using the C API and using C types? They're both wrapping a C library in a Python accessible API layer, right?
Kind of. So C types, if you split this up, a certain amount of your code is the code that does what you actually want it to do, and a certain amount of it is like translation layer code. And so if you look at it from a high level, you can either do that translation code in C or in Python or in something else, or some weird combination, which is the third one. So in a sense, in this one, you write that code yourself, or you have Python generate it. But it's in C, and it's speaking the language that the C interpreter does explicitly. Whereas what C types does is it specifies it in Python, and then under the hood there's libraries which do that in an automated way.
So C types, you define the API in Python syntax. In the C API, you define it in C syntax.
Yeah. It might be easier if I just show you. So actually, there's one more option. Do you mind if I come back?
Oh yeah, that's fine.
Okay. So, blah, blah, blah. Like I said, it's huge because we have to take care of a lot of maintenance. And so the last one is probably one of the more popular ones. It's CFFI. It stands for C Foreign Function Interface. So it's another way of automatically generating those, except it attempts to do so by parsing actual C code, which I'll show you in a minute. So again, we have the translation layer in Python. So it's approaching it from the Python side. You read the C source, and then that can get all of this gets compiled down into that binary. So in contrast to the actual C code, this is a subset of C, which is both good and bad, because it's a lot more concise than manually describing all of the bindings in the way that C types requires. But because it's a subset of C, it may take longer to do certain things that would be quicker to do in just standard C. So for instance, there is no preprocessor, so none of your pound directives work, including includes, defines, that. There's no type defs. So if you know C, this one is not a bad way to do it, but it's just more convenient if you type that into a shorter name. And so it's little things like that. But if you get it working, it is pretty fast. This was right up there with the amount of speed ups for the others. So like I said, it's fast, but it is not standard C. It requires learning how to do things a little bit differently. So that's everything. I was going to go into questions, but since we already have one, let's see. So did it a different way. just haven't used this software as much. So yes, I'm using Google Slides, which is not the most convenient version. All right. So here's why I have examples of example implementations of all this. So yeah, this is why I put them in the first one.
If you're able to unhide the slide and then present, that will work.
It's still gonna be too small.
Okay.
So this one's a
This-
little better.
So the slides are gonna be linked to on the meetup.com event page, so you'll be able to peruse them at your leisure.
Yeah, and I don't recommend going through all of them. This is not intended to be like a detailed, fine grained level thing. But what I was talking about when I said that this one had boilerplate was that each chunk of those is just one argument of one method. So all of that is for each of those is for one method. But it's for binding a method to the standard interpreter, which you've already defined in C. So it's not like interesting work, it's just typing and make sure that you type the right thing sort of thing.
Do you have a good resource to explain that binding process?
Actually, the documentation for C-types is pretty good. The hardest thing I had was trying to figure out what the use cases were, like why would you want to use C-types for CFFI, and like what actually happened under the hood. So that was a little bit of like wandering in the forest. But once you get there and you, like, say you've decided you want to do C-types, the documentation is actually pretty good. Like just the ones from python.org.
It's just you have to know C already.
Yes.
You should repeat the questions for the audio then.
Okay.
Just say it. Okay.
He said you have to know C, and I heartily agree. Yes.
So what happens if you malloc a bunch in the C side, and then, move those objects over to Python? Does the Python garbage collector assume ownership of that? Do you have to free them after the fact?
So I'm assuming you're talking about the C8. Thank you. So, question is, what happens if you malloc a whole bunch of objects and you're using the C API? I'm assuming.
Or C types or CFFI, if the answers are different.
So it depends.
I mean, in your C module, right?
So C types, one of the things that they do, the reason why those libraries exist, is because they take care of a bunch of that stuff for you. Most notably, memory management. So using C types is, it's a lot more like using actual Python. You just fire and forget sort of thing. But with the C API is the odd one out, and that's the one where you do have to make sure that you keep track of all that. And so if you pass it into the C API, and you don't free it, you now have a memory leak. Welcome to C.
What about the FFI?
Same, the memory management is handled by that.
Interesting. So it will like deep copy all the objects at the transition, or?
Well, so now you're getting into more subtle questions, like does it do a deep copy versus shallow copy? I don't know, I didn't test it a lot.
Or any copy.
Good question. He was first.
Just
So
had a
you
comment
then you.
on the C types thing. If you call malloc from C types, it won't free that unless you explicitly call free. Like if I do C types .dll open of libc,
Yeah.
libc.malloc of 500,
Okay.
I get back a care pointer object in Python, and it won't call free on that automatically.
Okay, super. Did everyone hear that, by the way?
Joe's point is that you sort of have to do the C stuff on the C side and the Python stuff on the Python side, and it mostly doesn't automatically convert between the two.
Right, so if Python receives a pointer from C code, it will not attempt to garbage collect it at all.
Right, it doesn't know what it is.
Right.
Right. Makes sense.
So yes, you can break C types if you want to.
Sounds like fun.
So Python is an object-oriented programming language, so it has its properties like inheritance don't have those things. So how to communicate? Suppose you implement inheritance in Python, and how those things gets.
Well, the long answer is you go look at the C API and it'll give you all this in very gory detail. The somewhat short version is that you basically write Python in C. So like where normally you have a duck type object, you now have a C pointer to something. And Jen, I mean, do we have any questions that needed?
I don't know.
I can bring it back up if you guys want. Yeah, so like you're really just talking about relatively large C structs, and they'll have a field for type, and they'll have a field for size. I didn't go really deep into it, so I couldn't tell you offhand all of those.
But a big part of working like this is, and it almost gets back to the previous question, is you have to do C kinds of things on the C side and Python kinds of things on the Python side, and it's not gonna automatically make it all work together. If you're using the C API with Python, then you're gonna be writing C code that's about Python concepts, and if you use C types, then you're gonna be writing Python code that's about C concepts, and that's just the way it is.
You're gonna get stuck re-implementing object-oriented programming in a
You might
basic
get stuck
programming
implementing
language.
object-oriented programming in C, yes. Get 2 more questions.
Yeah, thank you for presenting on this. It's very clear and concise. I was just wondering on like a high level if you had any more information on like the different the different performances you got from each one, and like why you think, like, you know, I think you said was the C types was the one that did the best overall, or?
Well, okay, so you're asking the question, if I have a business problem, what should I use?
No. I just wanted to know, like, how do you think the differences in the actual performance, right? So like in each test you listed the performance, like one was 83% faster, one was 87% faster.
Oh, like why was it
Yeah,
faster?
yeah. I guess on a high level, do you know why? I don't know why.
Most of them, no, I don't know. I would love to know, but you know, only so much time. The PyPy was the one that we did actually get prompted to look into, because the first time I ran it at a really low number of reps, and it was slower. And everyone I talked to was basically like, what's going on here? And then, so we look into it, it turns out that it has a workaround, and so you get that. Yeah, there's so many things to dig into there. It's a little bit longer
C types
conversation.
was the next fastest though, is that correct? Or in this particular problem?
For this problem, sure.
Okay.
You?
Sure. In your research, did you find any good example, like projects that would serve as good examples of real world uses of these? Like I'm kind of left with I'm still kind of left with the question of like why, and like what solution, what problems are people trying to like? Why do people use this tool? I mean, I know like a lot of projects do, and I understand that it's just like because it's faster, but for me, I use it. What's that?
We make real-time instruments on a BeagleBone, and Python takes 5 seconds to process 1 second worth of data. That doesn't work.
Okay.
So with C types, I can process 1 second worth of data in 1/8 of a second.
I guess I guess the question stands like, was there any? Did you find any like, if I wanted to go like look at real world examples of usage of these, were there any projects that stood out in your research?
Check out Pontopian open source projects.
Do you have any names you want to throw out?
Actually, yeah, like Zipline, the github.com/Pontopian/Zipline has a number of Cython modules. I don't think we're using C types or CFFI in that one. But we do use a good amount of Cython for speeding up of programs. And like, we have other projects worth doing.
Basically, anytime you have compute-bound code that you want to go faster, these are ways that you can do that.
I think like Pandas uses Cython, something like that.